Right, I'm just going to share my desktop just now with you. So hopefully everyone can see that. Okay, so today we're going to have a look at some future crypto. Okay, so you find that on the GitHub. Remember, you can have a look at the coursework, which is going to be a key focus of our work from now on. If you go into Z assessments there, you should find the coursework specification actually in there. Okay, so our normal Monday session will go ahead as normal, so we can have a bit more of a chat about the coursework and maybe do a few one-to-ones around your coursework. Okay, so before we start, let's do a little bit of an assessment here. Okay, so I've just set up a quick quiz for us. If I can just move this aside. If I can find the present button. There. Okay, so if you can just get connected to that. Do a quick survey on what things you've liked up to now, what you might do your coursework on, and things like that. Okay, so if you just get yourself set up. Just make a little start. Okay, so the first test looked at some fundamental areas, symmetric key, hashing, public key, key exchange. We've done a bit on digital certificates. We've done some blockchain and so on. Okay, so hopefully it's given you a basic foundation knowledge. In this area, you can never stop learning, and you'll find that once you understand a key concept, then it really just keeps building up on that. But without that solid foundation, then it's very difficult to build on sand. Okay, so let's go. Okay, hopefully I'll still show the little code there if anybody still wants to connect. Okay, there we go. Okay, which was the most interesting topic so far? Go and arrange them in order. Oh, blockchain, it's doing well. Oh, certificates doing well. That's really good. Public key doing not too bad. And there, public key doing well. Hashing not so well. There, tunneling. Oh dear, for tunneling. Public key. Oh, blockchain. So kind of fight between blockchain and public key. Oh, but public key is top. Oh my goodness, it's my favorite subject too. So public key is doing very well. Blockchain, key exchange. Oh, key exchange just dropped a little bit. We're getting a lot of love for symmetric key coming through. Digital certificates, key exchange, poor old tunneling. And hashing right at the very bottom. Okay, this I thought with all the hashcat stuff that would be interesting. Okay, so it looks like public key is, and I think hopefully once you've studied that, it really brings the whole subject alive, and you can see the potential of building a new world around public key. And it's great to see blockchain up there too, because obviously blockchain relates a lot to public key. And key exchange is obviously extremely important when we look at our tunnels and things like that. And it's going to become increasingly important. Symmetric key does well. Digital search in 5th place. Good to see that. Tunneling, not so much, and then hashing right at the bottom. Okay, so that's really interesting. Thanks for that. And which is your strongest area? Which area do you think you're best at? Which area in the test did you just wait to see the question coming up because you were all ready for it? Certificates is true. Yeah, generally in the industry, people struggle with digital certificates. So that's certainly a challenging area, and tunneling not so good. Oh, we got some love for digital certificates. That's good. But generally, public key is your strongest area, which is really amazing to see. Symmetric key, we'll do a bit of symmetric key today, a little bit of key exchange, a little bit of blockchain, not so much on hashing and certificates, and nobody thinks of tunneling. So probably because we didn't cover it in the first test, maybe tunneling isn't as strong an area. If you've got some time, so please have a look at SSL if you can. Okay, so for your coursework, I know you might not have locked down your coursework area, but which area are you going to pick? These are only some samples. You don't have to go with these topics. If you have another topic that you quite like, then it can be included in there. Not much love for homomorphic encryption or for tokenization. Maybe I can change your minds today. A little bit on key DCs. We'll be doing key distribution centers next week, I think. We'll be doing more on tokens and Docker next week. It's a really interesting area. Tokenization, very, very poor in the industry about the usage of tokens and one-time sign-ons and things like that. So a lot of love for lightweight crypto. Oh, got one there, another blockchain one. Closely followed by a bit of blockchain. Okay, so don't bite off more than you can chew, perhaps, with the blockchain things in there. Good to see some quantum robust and some zero knowledge proof in there. A little bit of homomorphic encryption and key distribution centers. And nobody wants to do any tokenization. That's part of the lecture for today. So maybe that things will change a little bit, and I'll do some tokenization next week on that. Okay, so given a language to implement your crypto, which one would you select out of those languages there? Don't see much love for C or C++. Wonder why. Wonder why. For lightweight crypto, it's difficult to avoid because it is a machine-ready language where Python obviously struggles to compile. Go is a great alternative because it does compile to machine code. And Node.js has really taken off massively in the industry. And it's a horrible language, but it's certainly supported by so many libraries. Okay, so hopefully we're all in agreement. Python is our friend. Okay, we might hate the syntax, but Python is a really great method to make things come alive. Okay, so we'll come back to this later, but we'll get our lecture done for today, and then we'll go back to that. So it's good to see that many of you have selected lightweight crypto as your preferred topic. Okay, so we're going to have a look at I'm going to do horizon scanning. There's no way I can cover these subjects in any great detail. Probably I'm just putting a seed of something in your head to be able to go and investigate for the future and to be thinking about how you can change systems and make them better. So we'll cover a bit of lightweight crypto, and then we'll go into some quantum robust, because obviously our public key methods are at risk and can easily be cracked by quantum computers. So we'll have a look at the contenders for a NIST standard. So NIST is standardized hashing methods with SHA-3 and then with AES for symmetric key encryption. And now they're looking at both at lightweight crypto standardization and also at a quantum robust crypto. So it'll be an interesting time to see which one is going to win, because they're going to do lots of tests and scorecards and do lots of security and so on to find, hopefully, the one that will move towards to be able to migrate away from our existing public key methods. I'll give you an overview of some tokenization, which is definitely happening. So many industries are tokenizing their data, transactions, and so on. Then give you a heads up on some zero knowledge proof, do some homomorphic encryption. Is it possible for us to process encrypted values and still add, subtract, multiply, divide, and so on if we have encrypted values, and make some sense of them? And then in the end, we'll have a look at what's called ZK snarks and some range proofs. Does someone have a question? Good. So please ignore my cat in the background. Okay, so we'll have a look at some lightweight crypto. Okay, so let's go back to a question. Was it someone with a question? Okay, let's go back to the very first lecture that you ever got on computers. Okay, I know that's probably quite a while ago. But what makes up a computer system? Let's say we have a processor, and we have some memory. What else have we got?
You've got the buses to communicate between all the hardware.
Yep. So we've got our data bus. And the other one?
Input, output.
Yep. But we've got our address bus. Okay. So each of those are a certain size. What's a typical size, do you think? Typical size of our data bus, say on the computer that you're running just now? Many bits?
64 now.
64, yeah. But it might also be running 32. It might also be 16, or it might even be 8, or it could even be 4. It doesn't have to be sort of big, because if we have 64 bits and we just have a little micro sensor, then there's no need for 64 bits. We might only need 8 or 4. Okay, so each of our locations in memory is addressable, and they're all addressable within per bytes. Okay, so we load up, we point to the memory, we fetch, then execute, and then we put the memory, we put the results back into memory. And some languages like C, we can get direct access to our memory through pointers, which has caused lots of problems because somebody just needs to overflow an area of allocation from memory, or even underflow it in them. So within the processor, what have we got? What's the core thing that we need in our processor? What's the magic that happens inside there?
It's like different layers of cache, I think.
Yeah, we have a cache, cache here, and we have a cache here, and so on. So the cache allows us to look ahead, predict what we're going to need from the memory, and fill that up there. But there's where is the program run? Where are the calculations actually done in?
It's normally done by hardware.
Yep. But there's
Right.
scratch areas. What's the scratch areas called? Can you remember? I know it's gone by.
Registers.
Oh yeah. It's probably too easy, too simple. Okay, and we've really came through a lot. Okay, the company who defined this standard was Intel. Like it or not, even Apple adopted the Intel architecture. Can anybody remember what the name is of the architecture is that we typically use?
x86.
x86 for what size of data?
32-bit.
32, well done. Or x
64.
68 or 64-bit. What a horrible mess that we've ended up. So we run programs that either run on a 32-bit model or a 68-bit model. The 64-bit model is obviously faster and so on because we can process more data. So the registers that we have in here are either 8-bit. I don't know if you remember your processor. those horrible lectures that you used to get on machine code. But if you remember, it was like AL was how many bits? Can anybody remember that one? 8 bits. And then there was a AX, which was 16 bits. And then there was SAX, which gives you 32 bits. And then obviously your registers can now be 64 bits and so on. Okay, so the machine level, the code itself was actually defining how much data it would actually support at any given time. Does anybody know the other architecture? If you have an iPhone or a Samsung, it's not using Intel. Do you know what?
ARM.
ARM, yeah. ARM dwarfs the other two. Generally, ARM focused on highly efficient code, which was power efficient, where Intel often just kept increasing the processing speed, made it faster and faster and faster, and it drained more and more power, which is fine when you have a power supply. But if you have a battery, then these hungry processors just eat up your battery like anything. And if you looked at my computer just now, it's probably sitting at 5% or 10%. So it's actually wasted to have all that grunt. It would have been better for me to have maybe some cores that shut down and so on. So ARM have generally been much more efficient with their processors, and now it's almost like becoming a de facto standard, and increasingly it's used. And I think Apple are going to move their Intel architecture towards ARM. So the next generation of MacBooks and will move towards the ARM architecture and move away from Intel. Okay, so that might all look great in terms of that might look all great in terms of our normal desktop processors and so on. But there's a whole world out there that's evolving, and it's evolving around IoT, sensors, RFID devices, and so on. And these processors aren't the big desktop processors that you get. They are fairly limited processors. So on something like an RFID chip, you might only have 200 transistors. You might only have a battery which powers up from the radio wave that you send to the RFID chip. It couples the power and then does enough to be able to send its message back again. So the crypto that we've built actually isn't fit for that type of device. If we look at something like this little chip here, hopefully this will show us an example. So this is an ARM. It's M3 is quite an old processor, but obviously it's inexpensive. Only costs you £5 there. It's a 32-bit processor, and it's only running at 8 84 megahertz. So not the 2.4 gig that we see for our processors. It's running at a much slower speed. The slower speed allows us to be much more power efficient. It only has half a meg of flash in there. So we're not going to be loading up big programs into a little microcontroller from there. If you see the RAM size, quite small, and there will be many more of these types of devices as there is opposed to our bigger processors. And this one here, I think is an 8-bit. That's the other one. I'll just see if I can get the other one there. Yeah, so this is an 8-bit microcontroller CPU, 32 kilobytes of flash. So you're not going to be loading up a lot of program there. So obviously the footprint makes a big difference. And it's only about £1 to buy this thing. The speed of the clock is only 20 megahertz and so on. So if you think you're possibly going to get AES to run on this type of device, then you might be struggling. But we can go right down to even smaller sizes, even smaller CPUs, and we'll generally struggle. So we can basically split our crypto into two main areas. There's conventional crypto, which is servers, desktops, laptops, smartphones. Your smartphone is a quad-core processor. It's actually very efficient. It has highly efficient processors in there, and it can generally do crypto. And then there's the lightweight crypto elements. That's related to embedded systems, RFID devices, and smart sensors. So the key ways that we assess our lightweight crypto is usually involves performance against performance and security. Of course, you take the two together, performance and security. And you need to understand what security level you need. Do you need 256-bit security, or is 30-bit security enough for you? So we take those and then we look at how efficient it is for a power drain, because a sensor might only have a limited amount of battery available. So we need to understand how much the crypto drains the battery. We also need to look at the number of gates, because eventually in a hardware type world, an embedded device has a number of gates. Each one of those electronic gates has a certain number of transistors. That leads to a certain size of a chip. So you might only have a certain space for your chip. So obviously the smaller you can make it, the better for that. Along with this, we need some memory. So when we load up our crypto, then it has a footprint both in the ROM or the flash area of the program, and it also has a footprint when it's running in memory. If we need great big buffers for memory and cache areas and things like that, then probably it's not going to be efficient. So we want to be able to bear down on our memory spaces and of our basic footprint. So one of the metrics that we use is a micron squared area. So if we were to implement this method of crypto, what size of chip would we actually need for certain types of manufacture? Okay, so on the website, I've got a whole lot of methods there. We'll have a look at the present method in a minute. What I've tried to do is to take standard benchmarks and make sure that they're actually working, because obviously what you've got to do with this is to take a key and a test string and make sure that you get an output crypto. You try a few and make sure that your code is actually working. the last thing that you want is to find out that you've been encrypting wrong, and you could end up with a whole lot of problems. What I've also tried to do is I've been using, to help support you, I've been using this Replit. And Replit allows you to put your code online so that you can actually prototype in there. So it should install all of the libraries and so on. Obviously, you can use your Ubuntu machine or whatever you have, but this is a convenient way for you to share code with me or for me to share code with you. If you have any problems, it's Python 3.8. I've tried to upgrade all my code to 3.8. It's taken me a while, but nearly there. And you basically just paste in your code, and then it'll install in any of the libraries that you actually need, as long as they're on PyPI from there. You can then run your code, change anything that you want in it, and then you can share. So it shares a link with someone, and they can actually have a look. The only problem is that it's a public repository, so that somebody could actually have a look at your code. So if something is secret, then you might want to avoid that, but it's quite easy to change your code in there, and you'll get your output from there. Oops, I've overflown that buffer there, and hopefully it should all work for you in there. Okay, so it's quite good because it gives you sort of hints for your code. So the places you would look is within GitHubs to be able to find robust code, and then to look at the test vectors to see how they're running. Anyone, any questions up to now? Good. Okay, so I've got some examples, and I've tried to take as many as possible. XT is the fastest crypto method around, possibly. Simon, Spec, LEDs, and Inokoro, Grain, and all these ones are block ciphers. These ones are stream ciphers. Obviously, the stream ciphers are faster. These are the hashing methods that are proposed, and we have a MAC. And there's not a lot for replacing public key encryption just now, so we're going to be struggling a little bit. Elia is the only one that I've found in there. But most of them are just focusing on symmetric key encryption and not bothering that much about the public key part. Okay, so when you've got time, if you could just have a look at some of those examples. And there, most of them are C++, which I know is horrible, but it's very difficult to avoid C++. But it's quite good to get running from there, and you'll find, so I've got the code. If we look at the Replit here, this is Klein, I think. And I know it's horrible. You've got to put your header files in and things like that. It's not a bad thing to at least be able to run the code. So when we run, Replit will automatically compile it to some sort of executable form on the server. Okay. But there's lots of things like make files you've got to make. But if anybody's struggling with any code, then just get in contact with me, and we can obviously look at getting it to run. Once you've got it to run, then obviously you then need to think about your experiments for your coursework. Okay, so this was this is from a paper in 2007. So things have kind of changed quite a bit since then. But I thought I'd just outline what researchers will actually define for the assessment of each of the methods. So we can see that they've all got different sizes of key size. So there's a paper published recently called Too Much Crypto. And Too Much Crypto says, why do we need 256-bit keys when it is just such a massive overhead, and it's almost impossible. You have so much headroom there that why don't you reduce the key size down to a manageable size, and you'll improve the performance overall. So in AES, why don't we cut down the number of rounds that we do? Because we don't really need this high security for an IoT type device. So some of the methods are using smaller key sizes, which are probably enough. As remember, 72 bits is where we are. So there's a good headroom there, and you would need a GPU and so on, and to crack one entity. So 80 is probably acceptable there. 56 is definitely not acceptable, but in some applications it could be fine. 80 sits there, 128, and so on. So there's our benchmark there with AES, and isn't it horrible in terms of its footprint? It has a big block size, 128, 32 bytes in there. It is chewing up lots of cycles per block. Just to process that block, it's going through every tick of the clock is a consumption of power in some way. So it's really eating up there. And the actual throughput of it is actually very low. It's quite inefficient. It's taken security to the max, but it doesn't bother that much about performance and so on. And it's taken up quite a large area on a chip with lots of gates. Over 3,000 of these logic gates are required to build it. If we look at something a bit more efficient, such as a 64-bit block size for present, so we're now only dealing with 16 bytes at a time, and we see the number of cycles per block to process is massively reduced, which means the throughput is at least nearly 20 times as much there as AES, and it also takes up a smaller amount of space on a device. Some methods are optimized for hardware. So they're designed exactly so that we can fit it into a small area, and some are more designed for software in there. So we can see the hardware focused ones and then the software ones. And again, they have basic performance tests. You can see this one does very well here. This one has the highest amount for cycles per block, but you can see there its code size is quite small from there. Okay, if you look at something like IDEA, it's only taken 20% of the code that AES would in running in memory. Okay, so here's an example of the present algorithm. So it's kind of like AES, but a stripped down version of it. In this case, each round that we go through has an S box and what's called a permutation layer. The S box takes up, as you remember, takes a byte. In this case, it's a nibble, actually. Nibble is only 4 bits. And takes that nibble in and then maps it to something else with the S box here. So these are the nibble values that we get. So if a 5 goes in to the S box, then a 0 comes out at the other end. C goes in, then in hex, and then 4 comes out in there. So that's the S box pattern. We take our values, our nibbles that we have for our data, and we put them through there. We then have what's called the permutation blocks, and it's sort of like a little scrambler, a shuffler function, and it remaps the bits that come out or the nibbles that come out onto a different part, and then they're all brought back in together again. So we go through that, and then at the other end we do the reverse and we only take parts of the key because the key might be 80 bits. We only take parts of the key each time for each of our blocks. Okay, does anybody have any questions on what we've done there? Good. Okay. Right, well, strap yourself in for the next part, which is quantum robust crypto. So the problem that we have with quantum computers is that because of the waves that happen, it is possible for us to factorize n into p and q by measuring wavelengths and so on. So it's a well-defined principle that the discrete logs, integer factorization, and elliptic curve will all be relatively easy to crack with a quantum computer. With symmetric key, we'll be able to do things faster. So the headroom will move from possibly 128 bits to 256 bits. So symmetric key will just generally ramp up a bit because it just makes it more difficult, but public key will be crackable. So the methods that are proposed are these ones, and they've been around for a while, but their time has really come. Lattice crypto, I could do a whole module on lattice crypto, but it's at its most basic, it is what's called learning with errors. It's been around for a while. If I have lots of points on a lattice, maybe I've got thousands of axes, and I create all these points, and I find a point, and then I put a little error onto that point, a small little bit of noise, and it moves that point away from the point that I've picked. That's the error, and I'm adding a noise factor in there. Then it's an extremely difficult problem, a well-known hard problem to be able to find in all of those points what the point is that I'm referring to with the point that I've actually got. So that's defined as lattice cryptography, and it's likely that that will be the winner. It's very efficient. Our small public key sizes are going to change. So elliptic curve, does anybody know what the public key size is for elliptic curve? What's the private key
256.
size? That's the private key, yeah. Public key is?
512.
Say again?
512, I think.
Yeah, that's right, yeah, and a wee bit more. So it's a very, very small key size. Obviously with RSA, we're looking at 2K, but we'll have to get used to much bigger. There was a paper that was really interesting. In a post-quantum world, RSA would require 1 terabyte public key. So my MacBook has 1 terabyte disk. I would need all of that to be able to support an RSA key in a post-quantum world, which is just crazy, and it's obviously not going to happen unless we can get disks that are a zettabyte or so. So we're going to have to get used to bigger keys, but lattice certainly gives us pretty good methods there. If you're interested, I've got some examples here of what a key would actually look like for your public key, and so on. There are other ones that come from telecoms and telecoms codes and what are called linear codes. They were used a lot in early telecommunications, and these are what are called code-based cryptography, and again are a hard problem even within a post-quantum world. Multivariate polynomial cryptography. I mean, you could do a whole MSc on these areas, so don't worry too much. But that involves using polynomials x to the 5 plus 7x to the 3 and so on. And you can do some really interesting things. It's a known difficult problem to actually solve. If I give you several polynomial values, it's difficult to find the value of x. So remember, we did it at school quite easily, where we had 3x plus y plus 4y is equal to 5, and then another one, and we could easily find for that. But with big polynomial values, it's really difficult to find the answer for that. And the other ones are what are called hash-based signatures. So these provide one-time signatures. So it's possible for me to create many private keys that I don't show you, but I'll show you my public key, which is the top of a Merkle tree. And I can show you how, if I take all these public keys and aggregate them all up to a final Merkle, then I can sign for data by taking one of my private keys and then showing you that it was one of my private keys by showing you the chain of the Merkle tree down to my private key, and you know that it was one of my private keys that I've actually selected. So that's used in IOTA, the IOTA blockchain network, and is known to be quantum robust. Does anybody have any questions about those methods? Good. Okay, so the other thing that's really taking off just now is tokenization. So tokenization really involves how we can tokenize our finance, our assets. The way we transact can all be done through tokens, and it will allow us to be able to preserve privacy and increase security. So Liechtenstein was one of the first countries in the world to draw up what's called the Blockchain Act, because they can see the rise in the finance sector. And obviously Liechtenstein is a safe haven often for finance, and they want to make sure that they are ahead of the curve when we move towards creating crypto assets. So a crypto asset is that if I buy a car, I will have the crypto asset, and it will be signed for me, and I can give it to someone else, and then we won't need bits of paper and wet signatures anymore. So they created a consultation and eventually created the Blockchain Act, which would allow for a full tokenization infrastructure of their economy. There are three main types of tokens. There's a payment token, of course, we can pay for things with our cryptocurrency. A security token. Security token is where you have an asset that can be tokenized, such as a car, or even when you buy a home, you can transfer the asset with your public key. And then there's a utility token. We're all used to using tokens now for bus travel and train and so on. The Blockchain Act itself is looking to create legal certainty in terms of the transfer of tokens, who owns them, and who is in possession of them. And it really defines the legal consequences of the ownership of the token, your possession of it, and how you transfer it. And really the whole legal industry tends to move very slowly. Only the other day, I got something from a solicitor asking for a digital signature. It's the first time that I've ever signed something legal through a solicitor from an online system rather than a photograph of my signature. Okay, so we need to understand also where you have a custodian. So someone might hold your crypto asset. So is it possible for us to pass that on to someone and hopefully for there to be no attacks in them? So if you're interested, you can read the Blockchain Act from Liechtenstein. It's written in German, I think. But these are some of the things here. And it really tries to clean up the crypto currency industry. So companies will be liable for losses and they will be audited and so on. So it doesn't do any good if you have keeping someone's cryptocurrency. If you've taken a copy of the private key, there must be some way to be able to audit that everything is correct. Okay, so increasingly we're seeing tokenization, but but inside any industry, we must have some sort of audit compliance. So without some sort of auditing and compliance regime within cryptocurrency and crypto assets, it's going to be really difficult to exist financially. So one way that we typically keep things private is that we have what's called a surrogate identifier. So the surrogate identifier is we just have a table that maps, say, someone's ID to a surrogate ID. So it might be their credit card number gets mapped to another credit card number which isn't theirs. Whenever we see the identifier, we go back to our surrogate table and we remap onto there. Unfortunately, this is a weak method, because if someone finds out what the mapping is, then you've actually revealed everything, and it's not too difficult to bring two data sets together and reveal what the surrogate table actually looks like. So what we could be doing, and it's well known, is that we could be trading with tokens. So when we go into casino, rather than carrying large amounts of money around with us, we cash in with our cash, and then we carry around tokens. If we lose the tokens, then it's probably not a great hassle for us. At least we don't lose all our money. So what we can end up is having a low security environment for our tokens, but when we increase the security in terms of anything that maps back to something real, such as our money. So for personal identifiable information, we can keep that behind an exchange. So we can have a place which is got high security, which keeps all the data, and then outside we just use tokens for all our transactions. Whenever we need them, we'll map back what's on the token to our bank account. We can do the processing behind the secure infrastructure, and we don't have to actually reveal. Because a lot of the times what we're saying is, does Bob have enough money to buy this car, yes or no? And the bank can do the processing on his personal account without ever revealing anything, and then we can get a signed attestation back that Bob does have enough money to buy the car. Okay, so this is what we end up with. We end up with a token that is hopefully been created so it can't be attacked in some way, and then it goes into the processing infrastructure. We have our tokenization server, highly secure data infrastructure. We pass a token into there, it does the magic, and then we get some controlled information coming back, and we can get our output from them. Visa have best standards, and obviously many of the banks are moving towards the tokenization infrastructure for their transactions. And this is the standards that are set. There is another one called the FIPS standards that banks often comply with. The higher the FIPS standard, the more secure security that you actually have applied in your infrastructure, and that's audited to make sure that you are complying. But basically, you've got the best standards for crypto in there. You have a way to create the tokens themselves, and there is a strong encryption used. There's a good, strong key management infrastructure in there. There's a credit card vault, which you want to protect as much as you can. And you have good, strong network controls in there, and you use strong encryption for everything that you actually do. Okay, so here's an example. Bob wants to buy an Amazon Echo for $100. He goes to the tokenization server, that's his card, and what they're doing here is giving him back a token with a fake CVV number. So he gives that token to the merchant. The merchant says, can he buy that, goes to the merchant acquirer, his bank, then goes to the tokenization server and asks if it's okay. There can then be a mapping back to his original CVV number, and we know that's okay. Anybody can look at that number and not actually know that that's his real CVV number in there. And the good thing is that the tokenization server could actually send back a message to Bob to say, is this okay? Somebody just bought an Amazon Echo for you, it's triggered on your account, or it could send a receipt back to him too. Okay, so in a tokenization world, we have signed tokens that are signed and trusted, so we can't fake them and so on, and they have the protected infrastructure. There's an interesting method called format preserving encryption, because we have a lot of these card readers which are old and are just looking for a credit card number that starts with a 4 and has a certain number of digits and so on. So if we want to fake that, then what we can do is that we can make sure that our encrypted format ends up looking like a Visa number. 4, I think, is for Visa, 5 is for MasterCard, and so on. In this way, we can actually preserve, in this case, Bobby, and we can use encryption to then map that onto something that looks like a valid name. So this creates, you can also create what's called a honey network here. You can have a whole lot of fake cards. You can, if you get your credit card details hacked database, actually it's very difficult for the intruder to tell what's real and what isn't from them. Does anybody have any questions up to now on that? No, good. Okay, so let's continue on a little bit, and I'll try and outline some of the other future areas. So we live in a crazy world where we pass passwords, we pass our date of birth, we pass our name, our GPS locations, and so on. Where most of the time, all the system needs to know is that we do know our passwords, and we do know that we live in Edinburgh. But we continually send passwords across the line, and there are many problems with that. So in the future, what we could get are what are called zero-knowledge proofs, and it's possible for us to create some sort of puzzle that we can solve easily. So if we know the knowledge, then if you give a challenge, a puzzle, then if you know the knowledge, say of your password, it's easy for to solve the puzzle and give back the result. But if you don't know the password, then it's too computationally difficult for you to actually create the result. So hopefully we'll see a rise in these zero knowledge proof methods. At its most basic level, it's a bit like the Alibaba cave. Where if you know the secret passwords, which is open sesame, then you can go into the cave. So in this case, we have Victor, the verifier, and we have Peggy, the prover. So there is a barrier in the cave as you go in, that if Peggy knows the secret password, she can open up the cave and go through. So the challenge for zero knowledge proof is that whether Peggy actually knows the secret password. So Victor looks away, and then Peggy goes into the cave on one of the entrances, and she'll stand here in this case. And then Victor shouts that she must appear out of one of the exits. Okay, so he shouts A, and Peggy appears. So has Peggy proven that she knows the secret password in this case?
No.
You got a 50-50 chance of getting it right, so go on. She's went into the cave, and she was standing there, and Victor shouts, appear from A. Has Peggy proven that she knows the password? Go on, someone take a guess.
No, I think no.
No, that's right, yeah. She has a 50-50 chance of getting it right. So the next time she goes into the cave, Bob asks her to appear from B, and she doesn't, she appears through A. So does Peggy know the secret passphrase?
No.
No. Okay, so she has a 50-50 chance, but every single time we send her in, then it's like a 50% chance, and then it's a 1 in 4, and then it's a 1 in 8, and then 1 in 16, 1 in 32. So after 1, 2, 3, 4, after 4 goes, she only has a 1 in 32 chance of actually getting it right. So at that point, Victor is starting to suspect that she does know the password, and that. So we can keep challenging and make sure that she has very little chance of actually being able to prove that she actually knows that. This is the core example that's given for zero knowledge proof. There's another one where you get snooker balls and you get one black and a number of red ones, and then someone puts them behind their back and then asks them to reveal 2. How many turns will it take to make sure that Victor knows that there are only red balls there, and so on. Okay, so with zero knowledge proof, we can actually start to prove that we know something without actually revealing it. And in this case, Peggy doesn't actually have to reveal the secret passphrase, but she can prove to Victor that she knows it. And it was Shamir who, yes, Shamir again, who came up, the Shamir, the S in RSA, was one of the first to come up with zero knowledge proof based on discrete logarithms. And so in this way, what we could do is that rather than in our traditional way of sending our password over and then adding salt and taking a hash, where we know that's a flawed method, is it possible for us to be able to prove that we still know our passphrase? So in this way, we do some sort of registration initially whenever we are creating our passphrase, and so Victor just stores a random salt value. Then, in the interactive way, he sends a puzzle to Peggy. Peggy does a little calculation and then sends back a number, and Victor checks that, and you go, yeah, that's your password. So every time we'll get a challenge whenever Peggy wants to log in. Victor sends a new challenge to her, and then she sends back the result, and everything's okay. When Peggy needs to reset her password, we go through this registration process again. But you can see that it's not possible to hack Victor's side because all he has is some sort of random nonce value that he stores that is going to be able to create the puzzle or the proof for Peggy. Okay, so if you're interested, I've got some code online to implement the very basics of the methods. There's the Python code in there. Not really that much to it, but it all should work, hopefully, from there. If we get a random value for the challenge, then hopefully at the end, it all works out. We can have Peggy with a different random value, and hopefully everything will be okay. Okay, so we Shamir came up with what's called the Fiat Shamir method, and this is it here. So I wouldn't expect you actually to see the details of the crypto, but have a look. Everything is done mod P, as you remember. It's our discrete logs, just like we had with our so we agree on a G and a P value at the start. From there, so we register that value, Peggy keeps a secret value, which is the hash of our password in this case, and sends over a value of y to Victor. She also sends over another value, which is a random. She takes a random value and then sends over that. Bob sends a challenge. She calculates this value here, and that goes back. And then Victor can actually prove that it's the right password. So the problem with this is that Victor's got to continually challenge Peggy for her password and give her a puzzle. So what we end up with is what's called a non-interactive random oracle. And in this case, we create our secret share, and then Peggy creates her own challenge, and then sends a response. So look, Alice never sends anything. Basically, when Bob wants to log in, he creates a challenge for himself and the response. So he sends the challenge and the response back to Alice, and then she just checks, and he can log in to the system without actually prompting him with a puzzle. Okay, does anybody have any questions up to now? Good. Okay, right. So let's ramp up a little bit more and look at what's called homomorphic encryption. It's a challenging area, and really we don't have the processing power around just now, and you probably need an IBM Z series computer to be able to get the grunt required to do a lot of the methods, but it's advancing quickly. The methods, there is a general move towards improving homomorphic encryption to be able to encrypt values and still to be able to process on them. So I think within the next 5 years, we'll see a massive increase in homomorphic encryption. And basically what it does is that you can take two values, you can encrypt them, and then Eve can add them together and get an encrypted value, which can then be decrypted. So the magic here is that we can use add, subtract, divide, and multiply as operators, but we can do that with inside our encrypted values. And we can also do things like find out if Bob is older than Alice without actually revealing. If we do a subtraction and end up getting a minus, say, then we know that Alice is younger than Bob without actually them revealing their ages. We could also work out how much income they have without actually revealing the days that they've worked and so on. And we can work out things like total income and so on. So in this way, we can actually do our calculations without actually revealing things. And it was actually Gentry, along with these other researchers, who came up with what's called full homomorphic encryption. Full homomorphic encryption allows you to add, subtract, divide, and multiply on encrypted values. We also get partial homomorphic encryption, where we can say just add and subtract or multiply and divide. Some of the methods like RSA and ElGamal are partial homomorphic encryption, so we can apply some operations. But if we want a fully homomorphic encryption method, then we need to use something like this method. In this case, we can take our encrypted values, we add in a secret key, we can go into a function, and we can do all our calculations in here, get the result back, and then we can decrypt. So we can have our data processor processing on encrypted values. So we could shunt off all our encrypted values to a processor externally, and even if they were to get hacked, they wouldn't be able, no one would be able to reveal the values. But when we come back, we can then decrypt them on our side. If you're interested, this is what happens. We take our bits, we break them down into bits again. We then put it into what's called a cipher circuit. And even if Eve is in this cipher circuit, she can't work out anything to do with the data at all. Everything looks like just random noise. We then decipher or decrypt each individual bit, and we convert them back into numbers in our data, and we get our output value. So this was the full homomorphic encryption method that was proposed here. If you're interested, it's actually very, very simple. Underneath, we take each bit one at a time, and we just cipher it with some noise, and it's possible for us to be able to recover that on the other side, as long as we have a secret value in here. Okay, any questions up to now? Good. Okay, so let's ramp up just a little bit more. So there's a method called the ZK snarks, and it starts to define whether it's possible, by not revealing any of the data, to make attestations. So is it possible for me to look at all Bob's transactions and determine if he has enough cryptocurrency to pay Alice without revealing any of the transactions at all, the values? So is it possible for us to look across all to do a tally of the plus and the minus to see that he has 10 Bitcoins in his account to pay Alice? And this way that we can create a zero knowledge layer, and we can prove things without actually revealing the data underneath. So ZK snarks is one of the methods that's actually proposed in this. And Zcash uses this method and uses it to be able to prove that Bob has enough cryptocurrency in there. The biggest problem with it is that it's really hungry in terms of creating the zero knowledge proof in the first place. Once it's created, it's very easy to then make that attestation, that proof, but actually to create the proof in the first place actually is quite a time-consuming job. In some cases, you've got to make sure that you delete your initial seed in a ceremony. So I think it happened with Zcash that they had to make sure that they lost all of the things that were used to create the original zero knowledge proof, because if somebody had that, they could go back and hack all of the transactions. Luckily, new methods have come along where it doesn't, you don't have to do that from them. So ZK snark is zero knowledge, succinct, non-interactive argument of knowledge. If you're interested in that. Okay, so what we can do is that we can mine across all our blocks, say for transactions, and they're all encrypted and we can't see it. We use a homomorphic additive function to do a tally of all Bob's accounts and find out with this new transaction whether he still has more than zero in his account. Okay, if you're interested, it uses a few different things. I won't go into the detail here, but it uses what's called hidden homomorphic encryption and blind evaluation as part of that. I've got examples on the website if you want to have a look at them in there. Okay, so as our last little part of this future crypto, we're going to be looking at what are called range proofs, petition commitments, and a few other little things that we can add to our toolkit. So as I outlined last week, Hyperledger is a great place for the toolkit. So you find a lot of the methods that we're outlining here are probably integrated into the Hyperledger project in some way. So it gives you a dependable proof. But often what we have is that we want to prove that something is a certain range. So can we prove that we're between 18 and 35 without actually revealing our age in between there? So range proofs are important to be able to prove that you are in a certain range of things without actually revealing things. So as you remember with our elliptic curve, as you remember, we have our generator point, we have our private key, and then we add G a number of times to give us privilege times G to give us our public key point. So what's a Peterson commitment? Well, this is our public key here. And what we can do is we can hide. So if we take our point and we add a random value onto it, we'll get another point on the elliptic curve. And it's not possible to find out the value that we've actually defined. If E is the value that we want to protect, then Eve could probably brute force that value to find the value on the curve. So if it's the number of bitcoins that we've paid, maybe 5 bitcoins, Eve would eventually be able to find that point on the elliptic curve related to 5 bitcoins. So with the Peterson commitment, we add on a random value, and the random value in this case is R, and it produces a new point on the elliptic curve. What we do is that we put the value of R into our wallet. So we introduce the concept of a wallet again. So the wallet, as we found last week, stores the private key, but now the wallet can be used to store these secrets that we have actually applied. So let's say that we apply this onto a blockchain at a certain time and make a commitment. Then nobody can actually find out what the value is that we've committed because they can't find out a random value. If someone wants us to now prove that, prove the actual value that we've transacted, we will reveal the secret to them and get them to apply the secret, and they'll be able to see the transaction that we've made, and it will prove that we made that transaction at that time, but not actually reveal it. It's a bit like making a bet before a football match. You would make the bet with a random value on it, and then after the match, if your football team has won, you would go back to the bookmaker and then say, here's my random value. I reveal that I said that Liverpool would win the match, and the bookmaker can't see the commitment beforehand, but then after, when I reveal the secret, that we can. So this has now been promoted as a method to protect bitcoins, and this person here proposed Mimblewimble. And Mimblewimble uses the concept of the Peterson commitment to be able to hide each of the transactions made on the Bitcoin network. And they even created their own GitHub with the code in there, Grin, for a minimal implementation of what's called the Mimblewimble protocol that would anonymize the transactions inside the Bitcoin network. Okay, so there's roughly what it is. We have a blinding factor R that's stored in your wallet. You have points in the elliptic curve, and then the R value is then used to blind the transaction until it's actually seen. And it was Peterson in his classic paper who actually created this. The other thing that we are moving towards is what's called range proofs. So in this case, is it possible for us to prove that we're in a certain range for our values, say for our salary? So you want to know that my salary is between $20,000 and $30,000, but I don't want to show actually what my salary is. I can actually create a signed proof it is between those values. And it's certainly used a lot with inside age verification. And it was created with one of the best methods around is what's called bulletproofs, and they are there to make sure that you can actually prove that your value is within inside a certain range, and you get a cryptographic certainty of that. So bulletproofs are short proofs of a transaction, and basically they can be used to be able to take all of the previous transactions that Bob has made, and then to aggregate them together, and then take the value of the current transaction and then find out if the value is greater than or equal to 0. And it's what's called the unspent transaction amount. As long as the unspent transaction amount is more than the transaction he's applying, then we can let the payment go ahead without actually revealing any of his transactions. Okay, so in this case, they're all blinded, but we can still tell how if Bob has enough in there using these bulletproof methods in there. And it's been applied into Monero. Monero showed a 80% reduction in the transaction size purely by implementing these bulletproof methods. So as I said, we can use it in salary checking. He needs to check that he has between 60k and 100k from his employer, and that he has at least £1 million in his bank. Say we could merge that into a single bulletproof and then give that to our bank so that they can actually prove that he has at least £1 million and his salary range is between 60 and £100,000 as a cryptographic proof. Okay, so they're designed really to be set up on a ledger type technology where we can quickly mine across anonymized transactions. And the good thing, as opposed to what we talked about earlier, there doesn't have to be a trusted setup with this ceremony. Everything will run itself. So we can actually prove things like that our bank at this instant in time has $1 billion in liquidity. It's possible for us to send that off to the FCA, say, to say here is the cryptographic proof that we have at least $1 billion in reserves, and there it is, and where fraud can be easily detected. Okay, so that was the coverage of the content. Sorry for the little interruption in between that session. Does anybody have any questions at all on what we've went over? I appreciate this a lot, but it at least gives you a basic understanding of some of the future methods involved. Anyone?
Yeah, I have a question towards range proofs. Can't Eve just narrow down the range more and more and more until they find out the actual value, like for the age, for example?
You can, yeah. So that obviously you wouldn't accept anything that you didn't like the range for. So if they asked you if you're between 18 and 19, you've got that's, I'm not proving that because that's not part of this transaction that I have to make. So you can take it down into maybe your date of birth within a year, but you've got to have a big enough range that preserves your privacy in some way, but allows you to define that it is within that valid range that you require. So you probably, and I mean a lot, and I think the kind of core around this is towards you storing your own credentials. So self-sovereign credentials allows you to be able to gather your own wallet with all these proofs in it. So you would only prove maybe the HMRC to prove your tax return range or something like that, and you can get these credentials that you can then show. And there are methods that can sign a whole lot of credentials, say by the government, and then you can pick off the one that you require. Say it's your date of birth or your year of birth, and then feed that off. So most credentials you just have a whole batch of them, where I think increasingly citizens can have their own credentials, because you continually log in to sites and you have to give away information again and again. So this type of method allows you to be able to create your own credentials that can be trusted and can be aggregated into some form that you can push. And if you don't have that credential, you've got to go back to the verifier and ask them to re-sign this attestation for you. And anyone else? Any questions? No. Good. Right. What I'll do is have a break for maybe 10 minutes or so to have a quick coffee. I'll stay online in this session, and then if anybody has any questions about the lab, so the lab should be on the GitHub. Have a look and see how you get on, but you can drop off the conversation if you want. But I'll stop this one and then I'll re-enable it again. So if you want to connect back in. Well, thank you so much. I know it's quite challenging to do this remotely, and please ask any questions. I'll have another session on Monday evening at 6:30, and we can talk a lot more about coursework, and then we can set up one-to-one sessions after that. As I said, we're now focusing on 70% for the coursework, so you really need to concentrate on that. We still have quite a while before the submission of the coursework, but please make sure that you make early inroads on it so that you know that you have a clear path for your submission. Okay, well, thanks very much. I'm just going to disconnect just now, but I'll start this session back up again in about 10 minutes or so, and I'll be around to take any questions that you have, really. If you have a previous lab that you're still doing, especially the blockchain one, I know that's not easy, or if you have anything related to the current coursework. Okay, well, thanks very much, and hopefully I'll speak to you all soon. Okay, thank you.